This lesson is about graphing. What is graphing? Suppose we wanted to consider this equation. Is this a true statement, x plus y equals 5? Well, it can be. For example, we all know that 2 plus 3 is 5, so it's fair to say that this statement can be true. If x is 2 and y is 3, this is clearly a true statement. Simple enough. So we consider x equals 2 and y equals 3 a solution to this problem. Another way mathematicians like to list this solution is as 2, 3 in parentheses. This is essentially called an ordered pair, where the x is the first number in the pair of numbers and y is the second number. So rephrased, 2, 3 is a solution to this equation. So how could we represent that graphically? Well, here's what mathematicians came up with. They decided to put a number line, call it the x-axis, another number line, call that the y-axis, and because we're trying to give a graphic representation of the fact that this statement is true when x is 2 and y is 3, considering that x equals 2 is here and y equals 3 is here, then this single dot, which is above the 2 and across from the 3, represents both pieces of information. In other words, that one single dot represents a single solution to this problem, the fact that 2 plus 3 is 5. But of course that's not the only solution. Clearly 4 plus 1 is 5. So if x is 4 and y is 1, we have another true statement here. We could put that in an ordered pair and consider plotting it the same way. Here's 4 on the x-axis, here's 1 on the y-axis, and this point lines up with both of them, and therefore represents the solution 4, 1. Let's examine one more solution to this equation. Negative 1 plus 6 equals 5, also a true statement. So when x is negative 1 and y is 6, the linear equation we're graphing is true, and if we put that in an ordered pair and plot that on our graph, we'll have another point that represents a true fact. Here's negative 1 on the x-axis, here's 6 on the y-axis, and this point lines up with both of them. And while we found 3 solutions to this equation, they're by no means the only 3, and if we were to take the time to find more solutions to this equation, and there's a never-ending list, an interesting thing would develop. All these solutions would appear to line up. And so what mathematicians do is they draw a line here representing essentially all solutions to this equation. And that's essentially what a graph is. It's a set of all points that makes an equation true. But guessing and checking, as we just did, isn't always practical. And in this video, we're going to learn more strategic and efficient ways to go about these problems, because they're not all this simple. Before we can get to those strategies, though, we need to discuss a quantity called slope. Slope is basically a measurement of how steep a line is. Here's an example. By the way, slope is denoted by the letter m, which I've never understood personally, but moving on. Here's an example. While this is the official definition of slope, it makes more sense to consider slope this way. A slope is a measure of when x increases by 1, it's a measurement of how much y is changing. And to get a better example of what that means, let's look at this line right here. Now what we're going to see in a minute is that this line has a slope of 2. Let me explain why. This triangle represents a steepness or a slope of 2 in the following sense. If we were to take any point on this line and increase its x value by 1 and its y value by 2, we would find ourselves back on the line. And that's what we mean when we say a line has a slope of 2. When x increases by 1, y changes by 2 or increases by 2. Here's another example. This particular line is going downward. When a line is going downward like this, it has a negative slope, and it turns out that this line has a slope of -1, as we're about to see. This triangle describes why that's the case. Because as we can see by the orange triangle, when x increases by 1, y drops by 1 to bring us back to that line. In other words, it's true between any 2 points on this line, if x increases by 1, y is going to decrease by 1. And that's what we mean when we say a line has a slope of -1. Let's look at a more complicated situation. This line right here happens to have a fractional slope, and quite often the slope is a fraction, and it gets a little messy. Watch how this works. This triangle represents a slope of 3/5 in the following sense. Here we have a point on the line. If x increases by 1 space, y increases by 3/5 of a space. Now, to make this a little bit more clear and to avoid fraction quantities like 3/5 of a space, which can get a little messy, follow me on this thought process. What if we were to continually go over 1 and up 3/5, and again over 1 space and up 3/5 of a space, and again and again? If we were to do this 5 times, mathematicians have discovered that it's equivalent to just going over 5 spaces and up 3. And this brings us to a concept that we call run and rise. In other words, if we have a slope of 3/5, while that technically means when x increases by 1, y changes by 3/5, it's actually more efficient to just think of it as when x increases by 5, y is going to increase by 3. Or restated, the run is 5 and the rise is 3. Let's look at another example of a fractional slope. This line is going in a downward direction, it therefore has a negative slope, and it turns out that the slope of this line is -1/2. Well, that means, as seen in this triangle, when x increases by 1, y decreases by a half space. And that brings me to another point on the line. And while there's nothing wrong with this, it's sometimes not convenient to think in fractions of spaces. And so imagine that we were to do that same process again, go over 1 and down a half space. That would be the same as if we went over 2 spaces and down 1. Again, reinforcing the concept of rise, a run being 2, and our rise being a -1 in this case. So now that we have a sense of what slope is, let's see how we can use slope to graph an equation without having to do a lot of annoying guess and check. We're going to start by studying something called slope-intercept form, and later you'll get a better understanding of why they call it that, but for now, consider the following problem. Suppose we wanted to graph y equals 2x minus 3. Mathematicians have discovered plugging in 0 for x will lead to a not only interesting but really useful shortcut. Watch this shortcut as it develops. If I were to substitute 0 for x and do some basic algebra, I would find out that y had a value of -3. Now, no one ever goes to the trouble to do this because of a cool shortcut that mathematicians have found. And essentially what they've found is that your graph's going to cross the y-axis at -3 in this case, or whatever that last number in the problem happens to be. So it turns out you can avoid all the algebra that you just saw by just knowing a shortcut. If this number here is a -3, your graph is going to hit the y-axis at -3. We call that the y-intercept. What about the other number in this equation, the 2? What does that represent? Well, it turns out mathematicians have discovered that that number represents the slope of the equation. And I'm going to use that slope to finish the graph of this line. We already know that this line hits the y-axis at 3, -3, and notice the dot down there. But further, knowing that the slope is 2, I can create my next point on the graph by simply having x increase by 1 and y increase by 2, thereby finding another point on this graph. And now that I have 2 points on this graph, knowing that we're graphing a straight line, we know where all the points are on the line, and that's the end of the problem. And this shows a really simple way to take the 2 and the -3 out of the equation, turn them into a graph, and not have to do a ton of guess and check. This slope-intercept form is called the slope-intercept form precisely for the reason that it has the slope and the y-intercept in it. You may be more familiar with the phrase y equals mx plus b, again m just being representative of the slope and b representing the y-intercept. Let's take a look at another problem, this time with a fractional slope. Suppose I wanted to graph this equation. Well, because it ends in a +5, in other words, because my b value is 5, I know that my y-intercept is 5. That tells me the graph is going to cross the y-axis at the dot that you see here. Let's further use the slope-intercept form by considering the slope of -3/4. That's going to help us find another point and complete our graph. What does it mean to have a slope of -3/4? Well, it's illustrated by this triangle here. In other words, if x increases by 1, y is going to decrease by 3/4 of a space. But again, it can be a little annoying to deal with fractional spaces. Now, there'd be nothing wrong with graphing the line at this point and saying, I'm done, I've graphed my line, and that actually is the correct answer. But for those of you who want to avoid fractions of spaces, here's an alternative. I could use the rise and run trick again by simply creating a bigger triangle going over 4 and down 3, thus leading to the next point on my line. And, as usual, once we have 2 points on a line, we know exactly where that line is, and we're done with the graph. Now, this technique is very, very helpful and pretty easy once you train yourself to do it, but it relies on the equation being in the specific format, y equals mx plus b, and that won't always be the case. So let's now examine a situation where the equation is given to us in standard form, which essentially just means the x and y term on one side and the constant on the other. You'll notice this equation is not in slope-intercept form y equals mx plus b. Now, there are other techniques to graph an equation from standard form, and you'll find those in other videos or courses. But for me personally, I prefer to take my standard form equation and convert it into a slope-intercept form equation. And by doing that, I can save having to know multiple graphing methods. So now the question becomes, how are we going to convert this formula into y equals mx plus b? Well, to do that, we have to get the y by itself. And no better way to do that than to add 2x to both sides, as you can see here. By adding 2x to both sides, I get a cancellation, and I'm one step closer to having y isolated. But to get this in y equals mx plus b form, I can't have that 3 coefficient in front of the y. So I'm going to choose to divide both sides by 3, thereby canceling out the 3. And a little bit of algebra later, we've converted a standard form equation into a slope-intercept form equation. And now that we're in a better format to graph, let's go about the graph. As you'll recall from earlier in this video, knowing that our b value is 4 gives us 1 point here, and knowing that we have a slope of 2/3 gives me a couple of options. One, I could go over one space and up 2/3 of a space, find my point and graph it. That is the correct answer to this problem. But again, to avoid fractional spaces, you may want to use the rise and run trick, creating a triangle with a run of 3 and a rise of 2, thus leading to a second point on the line. And as always, when we know 2 points on a line, we know precisely where it is. There's your answer, and this problem is done. So essentially, I approach graphing this way. If I have a problem in slope-intercept form, I graph it using the simple trick I've shown you in this video. But if I have a problem in standard form, or any other form for that matter, I will convert it into slope-intercept form and use the shortcuts in this video. There are, however, 2 situations in which you can't rely on any of the following or the previous strategies. One is if you have a vertical line. A vertical line always has an equation x equals number. So you can simply draw a vertical line in this case and say you're done with that. But let me tell you why that's the case, because if you know why that's the case, you're more likely to remember. So why would x equals 3, negative 3, represent a vertical line? And another valid question, where is the y? Notice there's no y in this equation at all. It simply says x equals number. Well, here's the logic on this being a vertical line. We all know where the x-axis is. We all know that this is negative 3 on the x-axis. So why are we graphing a vertical line? Well, here's the logic. Doesn't that black dot have an x-coordinate of negative 3? And doesn't this dot have an x-coordinate of negative 3? There's another dot with an x-coordinate of negative 3. All the dots that are appearing in this video right now all have one thing in common. They have an x-coordinate of negative 3. And so mathematicians have decided that x equals negative 3, for that reason, should be a vertical line. And that's the logic behind why x equals a number ends up being a vertical line. Here's the solution to that problem. And the last issue in this video is horizontal lines, which follow a similar logic. Horizontal lines, as it turns out, have equations y equals number, such as this one, y equals 4. And you could simply draw a horizontal line at y equals 4 and be done with the problem. But again, you'll be better served by knowing why that's the case, why mathematicians made that decision in the first place. Here's the reason. We all know this is the y-axis. We all know this is 4 on the y-axis. So here's something to think about. What do this point, and this point, and this point, and this point all have in common? Well, they all have a y-coordinate of negative 4. As does this point, and this point, and therefore the graph of the line y equals 4 is the set of all points whose y coordinate is 4, essentially this blue line right here.